All right, so we're going to finish our FBD packet number 2 with example number 7. So it says a block of mass 10 kilograms is on an inclined plane, which is 32 degrees above the horizontal. Calculate the force of static friction necessary to keep the block at rest, and then calculate mu sub s. So we started pretty simple with this packet, and now we're gotten to a problem that when you read it, there's lots of new vocab words in there, and it sounds pretty complicated. And that's why whenever you have a forces problem, you always use the 5 steps for success. Because that means, like, even an easy problem, you use the 5 steps. Hard problem, you use the 5 steps. It doesn't matter. You always have a system for doing these problems. I can't do every single physics problem with you, but I can teach you how to do some tough problems by using this method. So this is a tougher problem. So before we go ahead and work it through, maybe to sketch, we have the ramp again, just like last time, into our notes with the block on it. Then you try the 5 steps for success. And then when you feel comfortable, like you gave it a good attempt, go ahead and hit play. And then we'll be here and work it through with you. So go ahead, hit pause, and try this one out. See how far you can take it. All right, so we're back. So let's go ahead and do step number 1. So step number 1 says draw an FBD. So we're going to go over to our block. We're going to put a little point there to represent all the mass of that block at one point in space. And we're going to say what forces are acting on this block. And we're going to say, just like before, our weight vector always acts down, because weight is a force that always acts downward. So there's W. And then we're going to say, okay, it's on an inclined plane or a ramp. So just like when a block was on a table before, it has a normal force. Now, the one trick about the normal forces, when you have a ramp, is that they kind of go up like this. So I'll say boom. And that, if you draw it right, should make a 90-degree angle with your surface. So there's your normal force. Now, if we stop there, that would be the same exact problem we did last time. So this must be slightly different. So let's read it one more time. A block of mass 10 grams is on an inclined plane, which is 30. Blah, blah. Ooh, force of static friction. So here's the deal. In our previous question, this block was on a ramp, and there was no friction, which means as soon as you let go of the block, it's going to slide down the ramp because there's no force holding it up onto the ramp. But in this case, it's more of a real-world situation where this thing actually has kind of a frictional interaction with the ramp. So there's a force of static friction holding it up on the ramp. And you got to think back, well, static means that it's not moving, it's stationary. So let's go ahead and say, okay, the block wants to move down the ramp, but there's some force that's opposing its motion, and that's going to be your static frictional force, which we'll just label F sub s. And we know it's going back up the ramp because the block wants to move down. All right, there is step number 1 for success. Now let's do step number 2, which says pick a coordinate system. And you got to remember, for ramps, the block wants to move down the ramp. So then we decided last time we're going to define that way as the positive x direction, which means that our positive y is going up. So the time where we have what's kind of a rotated coordinate system is on a ramp. And that's just something you kind of have to commit to memory. And then step number 3. Step number 3 we did last time, and we hadn't done it up until when we started getting to ramps, but it says you have to do SOHCAHTOA for vectors that are not aligned with your coordinates. So let's just go ahead and check. Normal force vector is aligned with the y. Good. So we do not have to do SOHCAHTOA on that one. Your force of static friction is aligned with your x-axis, so we do not have to do SOHCAHTOA on that one. Your weight vector that's going down is not aligned with the x or the y because it's going through 2 dimensions. So just like last time, we're going to have to set up that same triangle for our weight vector, where we say this is the hypotenuse, this is this blue w vector, and we're going to go ahead and break it up. All right, so we're going to do our weight in the y. So something like that right there. So there's w sub y. So that's the weight that's in the y direction there, and then our wx is going to be right here. So there's wx, and then between those 2 vectors is the 90-degree angle. So basically what we have there is a right triangle that looks very similar to the one we had last time. And I'm just going to make a note. wx last time, our weight in the x, we said was going to be equal to mg sine of theta, and that's because our angle theta was right there, and this is the opposite side. And then we said wx was mg sine theta, and wy is going to be mg cosine of theta. So I kind of just always just remember that because I taught physics a long time now, but this that's across from the angle is going to be mg sine, because opposite for sine. And then the side that's adjacent is going to be mg cosine. All right, so step 3 is done. We did our SOHCAHTOA on the weight vector. Step 4 says to sum up your forces. So let's go ahead and say let's sum our forces in the x direction. So let's look. And I tried to color code them to make it a little bit better, but your normal force is right here. That's in the y direction. Wy, that's in the y direction. So the only two that you have in the x direction would be Fs and Wx. And you can see they're fighting each other. They're going against each other. So let's go ahead and say Wx is going down the ramp, and we've defined down the ramp as positive. So Wx is going to be mg sine of theta. And Fs is going to be negative Fs since it's going up the ramp. And those are our two forces, so I'll set it equal to Max. And in this problem, they say that the block is at rest. So we can set this equal to 0. Since it's at rest, that means the acceleration is 0. So what's kind of nice about this, mg sine theta minus Fs is equal to 0, which means we get a nice little equation that Fs must be equal to mg sine of theta. So there's the equation that we get from doing our summing of the forces in the x. All right, now let's sum our forces in the y. So in the y direction, you can see the normal force is going up and over to the left like this, and that's lined up perfectly with our y vector, so it's just n minus, if we look here, Wy, or our weight here in the y direction, which we said was equal to mg cosine theta, minus mg cosine theta equals May. And again, this block's stationary, it's at rest, so I'll set equal to 0 because the acceleration is equal to 0, which means that n is equal to mg cosine of theta. So there's another little equation that we have for this block. All right, now we did through step 4, so I got a little lazy here. I gotta put step 4, check. And sorry if that bugs you, I went pink, pink, pink checks, and then I did a blue check. Let's go ahead and solve this bad boy for whatever they're asking for now. A block of mass 10 kilograms, 10 kg, is on an inclined plane, which is 32 degrees. So 32 degrees is our angle. So there's our theta, it's 32 degrees. Remember last time we said that that angle right here is the same as the angle that's up top in our triangle, for our weight triangle, for our vectors. Calculate the force of static friction necessary to keep the block at rest. That means the block is at rest, so VO is equal to 0. All right. So for want, calculate the force of static friction. We want F sub S. Well, we don't have any kinematics equations from back in the day for an F sub S. So hopefully our step 4 equation's right here. And look at that. We have Fs equation right there we came up with. So for our equation, we're going to say Fs equals mg sine of theta, and then I believe we have all those numbers, so we'll say Fs is equal to m, which is 10 kilograms. Gravity, I didn't write it down because I was getting lazy. Can't take gravity for granted, but it's 9.81 meters per second squared times the sine of 32 degrees. So if you crunch Fs, you should get 51.99 is what I got. Newtons. So the force of static friction that basically holds that block in place is 51.99 newtons. All right. It says, then calculate mu s. So the next part of this is we want mu s. And if you think about this here, we actually don't have an equation anywhere for step 4 with a mu s. The only place I can think about getting an equation for mu s is, remember we wrote down a few days ago now, but Fs is equal to mu s times the normal force was one of our equations we did when we did our physics warm-up several days back. So let's solve this thing. So mu s is equal to, divide both sides by n, whatever Fs is over the normal force. Okay, well, Fs is equal to mg sine of theta from right up here. And our normal force, we have an equation for that right here. So normal force is mg cosine of theta. Ooh, that's kind of nice. Mg on top and bottom is going to cancel. And then we're just left with sine of theta over cosine of theta. Which, if you're a math all-star, like you're a physics all-star, I know there's somebody out there that knows what sine over cosine is. But there's actually a trig identity that says sine of theta over cosine of theta is equal to tangent of theta. So, to get mu s, we just have to do the tangent of whatever angle they gave us, which they gave us 32 degrees. So if you're in degree mode on your calculator, and you take the tangent of 32 degrees, let's see what we get. Tan 32 degrees, 0.62. And we'll say 0.62. And then units for this coefficient, there are no units, because it's just a coefficient. So, final answer from u sub s is 0.62. So again, is that a lot of work? Yep. But that's why we're kind of slowly going through these problems to make sure slow and steady kind of wins the race. We understand what's going on. And if you do take college physics, this is where it tends to get tough because your professors will go pretty darn quick through this stuff. So if you ever do take college physics and you're doing problems like this, just come back to these videos, come back to your notes, and make sure you do save these note packets. So nice job on this one. Have a wonderful day, and go Physics All-Stars.